Hello everyone, this is Ehsan. In this video we are going to compute the square root of a certain value. Here the value is given as a double or a real number which we model as a double. We could have modeled it using a float, however we decided for a higher precision, so we chose double, and it will return the result as a double. Initially, since we just want to test if our structure works, because we have designed it in a top-down fashion, we return 0 to see if it works. So we give the value, so this program computes the square root of a real number. We entered the value, let's say 5, and we expect the result to be 0 because it does nothing. So okay, it works so far. So now we need to change it. We need to somehow compute the square root of a value. Let's imagine that we want to compute the square root of 0. So the square root of 0 is 0, and the square root of 1 is 1. However, the square root of 5 is something in between 0 and 5, inclusive. So this not only includes 0, but also it includes 5, because that way we can generalize this whole problem here. So what I mean by that is it will not only work for 5, but it will also work for 1, it will also work for 0. So the question is, how do we find the square root of 5? And we know one declarative fact about this. So we know we have a declarative knowledge, which basically states that states a fact. So it states a fact that square root of a number x is y, such that y multiply y is equal to x, where y is greater than or equal to 0, meaning it's a positive number. So the idea is, if we can find a y when it's multiplied by y itself is equal to x, we know that we have found the result, and the result is y. However, it does not really help us find the value y. So it provides us with a test, but it doesn't give us an information about how we can find this guess or this value y, which when multiplied by itself becomes x. So for that we need something called imperative knowledge. So imperative knowledge, which basically provides a description about how we can deduce this value of y. So description about how we can find the value of y. And if we look at this carefully, this notion carefully, if there was a way we could start with 0, so as our initial guess, and then gradually increment the value of 0 to be like 0.0001, and then maybe 0.0002, and we test all the numbers in between with an increment of 0.0001. At one point there will be a value when multiplied by itself will be very close to y, and we need to find that value, and we need to somehow say, how do we define by how close the number is. So what we want to do is we want to say that double closeness is equal to 0.01. So if we can find a number which is when multiplied by itself is close to the value within the range 0.01, we say that we have found the value of y, and that's the result. So for that, what we do is we use a for loop, because so the reason why we are using a for loop is because we know when to start. So we start 0.0 and we end at 5.0 when we want to compute the square root of 5. So what we do is we say for guess is equal to 0.0, which is our initial guess. We check if the guess is less than or equal to value, because we want to compute till the end. And then we increment our guess by previous guess plus 0. So we increment it by 0.0001, and we remove this part. And then what we do is compute the difference, or compute the closeness. And one way to do it is we say the error is equal to guess multiply guess minus value. And since we don't care about whether the guess is positive or negative, we just only care about how far it is. We don't care whether it's left or right of the numbered line. So we just have to take the absolute value of the error. So ABS error is equal to absolute value of the error. And see here, the absolute value function is not written yet. We are going to write it, so it's a top-down design. And we say if the absolute error is very close or less than the closeness factor that we have selected, we say that we have found the value that we are looking for. We return the guess. Otherwise, it increments by 0.0001, and then we do the whole process again. And if we don't find it, we say we did not find it by returning -1, because square root cannot have a negative value. Square root of a number cannot have a negative value. Well, square root of a positive number cannot have a negative value. So when we see this negative value, we know that we did not find the result. So to initialization, we have to do is we say the error is modeled as double, and we say initially it's 0, and then we also model absolute error as double and initialize it to 0. And maybe we can, for display purposes, place it like this. So let's check. Everything seems fine. Let's run the code. And it says guess was not declared in scope, because we did not initialize. We did initialize guess, but if we did not model it properly, we have to say that guess is double. We run it now, and absolute value was not declared in scope. So I forgot to actually create the function which computes the absolute value. So we do it before like this, and we say returns a double. This function returns a double while taking a double value, and the function is if value is less than 0, return the negative of the negative number, which is a positive number, or if it's not the case, then just return the value because it's positive. So let's run this, and we give the value of 5, and we see that the answer is 2.2339. And we can actually check this if let's do it here. Google Google is here. I say sqrt of 5 is, well, it's very close, it seems. 2360, and we got the value 2339. Very close. If we change the closeness then and change this guess incrementation method, it will go closer, but let's keep it this way so far. So this thing works. In the next video we are going to show a better method to compute this. Well, before I move on to the next video, I just want to add one thing, is that if we want to check how many times we have actually guessed, have to make a guess, we can actually see that. So we can do it like, say for instance, I would say int num of guesses is initialized to 0, and then we do this. If we reach at this position, we increase the guess, and we want to show how many guesses we have made. So we say cout number of guesses to the solution is num guesses solution is num guesses, and we say NL here. We put quotation sign here, and we copy all this thing over here, Control V, and then run it again just to show how many times we had to guess. So let's say 5, and the number of guesses that we have to make was 22,339. And if we change this increment by 0.01, and we also change this closeness factor to our higher precision value, maybe we increase this to 0, and we run this, and let's say we do 5. So you see now the result goes very close. However, the number of guesses that we had to make was huge. In the next video we are going to do something which will reduce this number significantly.